Another interesting behavior of functions, polynomial functions that are smooth, continuous curves like these ones, is that very often these functions have relative maximum and minimum points that we're interested in finding. So the question here might be, given the definition of our intervals on which a function is increasing and decreasing, how can we figure out whether a function has a relative maximum or relative minimum? Well, here is the definition. Let's say there's an open interval I containing some point c on which f of c is less than or equal to f of x for all x in that interval, then f of c is a relative minimum. Well, we kind of have this mental picture of what we mean by minimum, so let's talk about this on a graph. There are several points on this graph that we might consider minimum. Let's look at them. In this one, x1 could be considered a minimum point, and the reason why is that we build some small interval. We'll call that interval I. We're just giving it a name, that's all. So on this interval I1 right here, we look for all of the values of f of x in and around that point. We say that the point x1 represents a relative minimum because if we compare the y value that we get at f of x1, we see that the values of y near f of x1 are less than or equal to all the values of f of x near that point. So in the vicinity of that interval on I1, f of x1 is less than or equal to all the other values of f of x near it. Therefore, this represents a relative minimum by the definition below. Right? Where are some of the other relative minimums? Well, there's one right here at x3. This is a relative minimum because on the small interval containing x3, f of x3 is less than or equal to all the other values of f of x near it. We'll make a little interval called I3 right here, and we're just containing a little area around that point. Right? Now we could make those intervals arbitrarily large or small, but on that interval, small enough to contain x3, we can see that f of x3 is less than that. F of x5 also represents a relative minimum in that regard. Now, if there's an open interval I containing some point on which f of c is greater than or equal to all the other f of x in that interval, then this is called a relative maximum. So x2 is a good example of a relative maximum. We say relative because we look around on this graph, and if we were to continue to the left or right, this graph might continue towards positive infinity, but in the close vicinity of x2. So build a little interval right here, we'll call it I2. On that small interval I2, we would see that the value of f of x2, the value of y at the point x2, is greater than or equal to the other values of f of x in the vicinity of that point. Our other relative maximum is found here at x4. So we would call that a relative maximum in that same regard. So when we have a picture of the graph, we can actually tell a lot of information about relative maximums and minimums of the function. All right, well, let's assume that we do have a graph of a function that might describe this one. A rectangular piece of cardboard that measures 10 by 12 inches. We're going to make an open box by cutting out equal squares of measurement x by x inches from each of the corners, and then folding up the sides. So here's a picture of the cardboard. We make this cardboard itself 10 by 12 inches, but then we're going to cut out pieces from it. So this is 10 inches right here. And of course the height of the box, where's my pen? There it is. The height of the box itself of the cardboard is 12 inches right here. So we might be interested in looking to see what happens right here when we're trying to cut up this box. Well, we need a function to describe this. So let's put one together. what would we say? Well, it looks like our uh, conditions here are such that if we took this 10 inches, we would have to subtract 2x inches to get the measurement from side to side right here for our length. And if we go up at bottom to top right here, let me see if I can get a good position right here. From bottom to top right here, we would have to take 12 minus 2x inches. Why? Well, remember that each of the corners themselves are x inches here. Right? If we take each one of these, we're cutting out an x by x corner in each side. So each side right here is going to have an x inch corner cut out. Right? So it's 2 x's on each corner. So what does that mean for us? All right, well, our function should look something like this then. 10 minus 2x times 12 minus 2x times x, which is the height, right? Volume is equal to, and that is our volume function, v of x. Let's see if I can fix any of this function right here before I start going on any further and trying to write on my board here. All right. So if I work this out, what function do I get? Well, I've worked this one out myself, and I got 120 minus 44x squared x, pardon me, plus 4x squared all times x, get my pencil here working, still v of x as our function. Now what does this give me? Well, down here, if I work this out, v of x is actually equal to, and I work this down below here, and I'm just going to get my marker working right here. I work this out down below right here, and I got this function. Y is equal to 4x cubed minus 44x squared plus 120x. So where would the maximum occur? Well, here's a drawing of the function itself on the interval from 0 to 5. Our interval, the only values of x that would work right here are values of x that fall between 0 and 5, because our box cannot have corners that are any smaller than 0 or any larger than 5 inches. So if we look at our graph right here, somewhere on this interval, there is a relative maximum volume of our box, and it appears to be just shy of x equals 1 and x equals 2, somewhere in between there. So what we would say is that if we work this out, there's a way in calculus to do this. I'm just going to show you right here that at the point x equals 1.81 inches, we will have found that point in which the function has a maximum volume according to the formula that we worked out above. Okay, more to come in the next video.